on tomorrow on the 17th during morning session of weldability, because properly we need to understand the concept of the weldability. So how the American Welding Society defines it. It defines as a capacity of a metal to be welded under fabrication conditions imposed into a suitable design structure and to perform satisfactorily in the intended service. So it is a complete definition. It reflects the behavior of a metal or the capacity of a metal, and the fabrications condition is imposed is by the arc welding processes, right? Or the processes we go for, right? Whether arc or fusion welding processes or solid state welding processes, and into a suitably designed structure, right? So for the intended structure, it should perform satisfactorily for the intended service application. The service applications may be in a different area, maybe high temperature, low temperature, cryogenic temperature, maybe of room temperature, and for different parts and components. There are other definitions other than AWS definitions to understand this term weldability. So in other term is also known as ease with which a metal can be welded to give the required service, right? Simply speaking, or the weldability is the amount and nature of the problems you face to weld a material. Because when you are going to weld carbon steel, low steel, stainless steels, nickel-based, or say many metals and alloys, and the dissimilar metals, normally we face problems of weldability. What are the problems? We'll also see this problem. And third, again, it can be also defined as the ability of any material, usually metals and alloys, to weld with other materials. Now its ability to be combined or to be compatible with the other materials is also known as weldability. And weldability is the behavior of a metals under welded condition and during service conditions. That is more important, because behavior of metals, because materials behave differently when it is subjected to heating and cooling, and the thermal cycle. All of you are well versed with the welding processes, the fusion welding processes. So it's all about heating and cooling and the composition of the metal. So under the welded condition and during the service condition as well. Now during service conditions, temperature, the environment, be it different service environment, right? Service environment may be a corrosive environment, maybe high sulfuric environment, sour environment, different environment. Okay. Let us move further. I think my slide is not changing. Let's wait. Okay. Again, finally, there are also other definitions like weldability is most often used to define a material's resistance to cracking during fabrication. Now, this is where the development of various tests are there, because we need to find out the cracking susceptibility or the resistance to cracking during the fabrication. So what can be called as a good weldability, which is more resistance to various forms of cracking during welding. It's requiring essentially no work or no repair, right? So we can consider a good weldable material. Then, okay, then let us go through some issues in weldability. So I'm not sure whether there are previous speakers have told sufficient about the weldability issue, but I have thought to slightly touch upon those things to understand the test of weldability and quantifications. Okay, anyway, so you have, that the cracking, right? In the previous slide only, I come across a word known as resistance to cracking. Now, the cracking can be with the weld, can be with the heat affected zone. If the cracking is the weld, it is most of the time known as solidification crack or micro fissuring. And if it is in the heat affected zone, there may be due to hydrogen induced cold cracking, known as hydrogen embitterment cracking, right? Maybe because of liquefaction cracks or reheat cracks. Now, let me tell you something brief about the cracking in the weld. When it is in solidification cracks, sometimes when the most of the time happens in the root pass or in the center line crack because of the particular, say, in the austenitic stainless steel or welding, most of the time, when, or in non-ferrous aluminum or in nickel-based alloy, right? So in austenitic stainless steel, the phenomena is when there is no sufficient delta ferrite in a solidifying weld metal, right? 3 to 8% most of the time, and if there is no sufficient ferrite in the solidifying, then the solidification crack may take place. Otherwise, there are many issues with carbon steel and low alloy steel, particularly during because of the impurities, because of the low melting point, presence of low melting point tactics or low melting point elements into the solidifying weld metal. They weld the liquid boundary, they weld boundary with the liquefaction. Then in the heat affected zone, hydrogen induced cold crack. So sometimes during welding, when there is no sufficient uh, shielding to the molten pool, not either by flux or either by the shielding gases, then the hydrogen from the atmosphere will react with the molten pool, and you have every chance that this hydrogen, atomic hydrogen gets diffused in it. So this molecular hydrogen, particularly from the air, gets dissociated into the molecular hydrogen gets dissociated into the R by coming in contact into the atomic hydrogen. So these get diffused, and during solidifying weld metal, this hydrogen cannot get chance to escape out of the solidifying weld pool. So as a result, it traps there, and such H plus ions in a susceptible microstructure like martensite develops cracks, right? Because they occupies more space on becoming molecular hydrogen. So now liquefaction crack has something to do with the if there is a more solidification temperature range, particularly in the fusion zone and the heat affected zone, right? And when there is a more amount of low melting point eutectics under the contracting stresses most of the time from the fusion zone and heat affected zone, there will be separation through the crack. So it's known as liquefaction cracks. And for liquefaction crack to occur, solidification temperature range is responsible. It means higher the solidification range, higher will be the liquefaction crack. Then reheating crack phenomena occurs most of the time in ferritic steel, like chrome moly steel, wherein there will be some because of during the post-wear heat treatment, there will be relaxation of stresses, and the grain boundary becomes weaker, and there will be a crack through the grain boundary known as reheat cracks. Now there are other issues like porosity and oxidation of reactive metals, particularly when you're working with aluminum, nickel, it's quickly form oxides like L2O3, then NiO, then Ti, titanium. Okay. Paraporosity has the same with the maybe because of oxide porosity, maybe because of hydrogen, maybe because of nitrogen gas most of the time in nickel-based alloy and all that. So there are various issues. We will go through some issues, then we see the particular test to assess the weldability. Then again, the reduced joint strength in the weld and heat affected zone, that is more concerned with the precipitation or hardened precipitation aluminum alloy, right? Where there'll be a strength mismatch between the weld and heat affected zone. And there comes reduced corrosion resistance. This is the consequence of this weldability, because most of the time, if you have heard of weld decay, you know it that because of the carbon from the if there is a more carbon, if it is not a low grade stainless steel, then the carbon can combine with the chromium from the vicinity of the grain boundary and forms a grain boundary. It forms a intergranular cracking. So it's a reduced corrosion cracking. So it's a phenomenon known as sensitization. Sorry, sensitization of the weld metal. Okay, now I have some of these example of weldability problems. So oxidation of reactive metals, most of the time I have mentioned you aluminum, magnesium, and titanium. So you have to provide proper inert gas shielding and active fluxes. Then gas metal reaction or dissolution, most of the time, weld pool is not protected. You have a porosity due to nitrogen in steel and oxygen in carbon, nitrogen, and due to hydrogen, you have porosity in aluminum and nickel based alloy. Then there'll be a vaporization of low boiling metals, right? So porosity in the zinc process that may happen because zinc evaporates because of its low melting temperature, like 440, 450 something. Zinc evaporates very faster, so it leaves behind the matrix of copper. You have a porosity problem, so you have to use steam bronze filler in low currents. And hot cracking in weld, as I mentioned, due to low melting constituents and impurities of alloy element like sulfur, phosphorus, lead into the weld metal. These low melting impurities are segregated into the grain boundary. They form a liquid film. So under the cooling stresses, there'll be separation of the grains to the grain boundary, and you have a cracking. So you have to use two-phase filler metal SS electrode with sufficient amount of ferrite, and there'll be hot cracking in the heat affected zone. Maybe due to liquefaction in heat-treatable alloy, and cold cracking. Particularly, cold cracking is term used associated with the hydrogen cracking. Most of the time happening in the carbon, manganese, and alloy steel. So we have to use a low hydrogen electrode practice and preheat to control the cooling rate, and reduction in heat affected zone strength, particularly with precipitation or edge hardenable alloys. So we have to control the heat input so that we can control the cooling rate, and solution or annealing heat treatment after welding is recommended for those steels. And reduction in corrosion resistance is due to chromium carbide precipitation, as I mentioned you. So we have to use stabilize or ELC, extra low carbon grade steels. Now, having understood the various weldability problems, right? So it becomes now important to understand the behavior of a material during welding or after welding during the service application, right? So weldability is a process related. One of the statement or one of the important finding is weldability is a process related. How? Because the fusion welding process involves high heat input of the arc or from the heat source. So there will be a solidification of the molten filler metal, and fused base metal will be separate. And the heat affected zone. Heat affected zone is developed because of the thermal cycle. So metallurgical effects is both on heating and cooling, because during welding material is heated up, during cooling it contracts. So is expansion and contraction also producing residual stresses, as well as the material's grain structure is also affected by the thermal cycle. So there is a metallurgical effect due to the heat input is what I want to convey. Now, materials grouping for weldability. Now, from the practical point of view, when we refer ASME Section 9 or their equivalent ISO 15608 standard, depending on the characteristics of the material, like their weldability, assignability, and mechanical properties, these ASME have assigned a different numbers to ferrous metals in their according to their specified impact test requirement into the group numbers within the P numbers. So the P number, and G number, right? So by keeping in mind these behavior of metals, their weldability, brassability, and their mechanical properties. Like this slide shows, like the steel, for example, in SME Section 9 code, it contains the EP number from 1, 3 to 11, where is an ISO code. Likewise, you see the steel, aluminum, copper, nickel, titanium, zirconium, cast iron. So they are grouped depending on their uh, buildability, right? Why they are grouped? Because the fabricator would find it easy uh, to compare or to join two dissimilar metals and select their filler metal accordingly, right? Now, let us go through some pictures on weldability problems. That will be more um, interesting to know. So, on the first picture, on the top first right, first figure, you see hydrogen, it is called cracking picture. You see literally a crack, right? That is known as, that crack is in a HZ, hydrogen, sorry, that crack is in the heat affected zone, right? And it is also known as delayed cracking, right? Then second is a hot cracking in the weld. That is a center line cracking. You see a two plates joined by this weld joint. And you see at the center, right? There is a literally you can see a center line crack. This is solidification cracking. And in the third figure, you see a very crack, very straight crack, right? Almost a this crack is a lamellar tearing, right? That is most of the time found in rolled steel or in a steel containing some amount of non-metallic inclusions. So this is a lamellar tearing, this picture. So I wanted you to introduce these pictures so as to understand, as to better explanation of the weldability issues. Now we will move on to our main topic. So now by this time now you better understand this. There are many issues. Actually, I could include on many 3, 4 pictures and many such many such detail of the weldability issues. So now we'll move to our part on the classification of the weldability test, how they are being classified, right? And their classification is very logical nature. So first weldability tests are classified into 4 theoretical tests, sorry, into 5 uh, sub tests: theoretical test, simulated test, visual examination, component sampling test, actual welding test. Now, the actual welding test again is bifurcated into fabrication weldability test and service weldability test. Now, this actual welding test, fabrication weldability test, and service weldability test are of our most interest because this theoretical and simulation and visual may or may not give the clear picture of the weldability or the behavior of metals, right, during welding. So this is of more accurate to go for fabrication weldability test and service weldability test. Why go for actual weldability test, right? Sorry, why we should go for actual weldability test? That is that reason I'm going to explain just now. Actually, my slide has, yes, why preferring actual weldability test? Because the theoretical weldability test have that does not take into account all the welding variables, right? Like in a previous slide, I'm going to explain some say theoretical calculations. Now, I think we'll be able to understand better after this slide only. So you can see that these carbon steel and low alloy steels, their weldability is judged by empirical formula. It is well established, known as carbon equivalent. It is a formula reflecting the composition of the steel: carbon, manganese, chrome, molybdenum, silicon, nickel, copper. So you can understand these are the alloy elements having an effect on their weldability. So higher is the hardenable the material, right? And higher will be the susceptibility to brittleness. and at the same time lower will be the weldability. So it's a thumb rule, right? So for example, if you calculate the composition of your base metal and you find that your carbon equivalent is less than 0.35, or it is between the 0.35 to 0.55, right? Then you can say you, or sometimes less than 0.55, right? Then you require preheat or post-fire heat treat to successfully weld the material. But if it less than, say, more than 0.5, then it would be difficult to weld without cracking. It means either you have to go for some um, uh, high alloy filler metal, you have to use some techniques, or you have to go for different welding process. I mean, the fusion welding processes will not work there. You have to go for the solid state welding processes like friction welding, or say flesh butt welding, or likewise, right? So this is about a uh, very important say benchmark on the assessment of the weldability. Okay, Sarki asking something. Sorry. So please move your person downward top from the screen. So Webex for profile minimize. Okay, okay, sir. I noted down. No problem, sir. Okay, now I think now screen share will be working. Okay, so next concern is a dilution. Dilution, particularly, is is something, when you are, for example, if you look at the picture, if you are joining to say dissimilar base metal like A and C, these are two dissimilar in base metal in composition, and you are going to join it with a say filler metal, right? Now, this dilution can be calculated using contribution of the base metal into the weld metal. So A plus C divided by A plus B plus C. So A plus B plus C is a total fusion zone. It's a fusion zone, fusion zone chemistry, right? What will be the contribution of base metal into the weld metal is a percentage, is known as percentage dilution. Because during welding, what will happen? This melting surfaces edges will also contribute into the weld metal. So they contribute according to the process and the heat input, right? So if you are not performing welding with filler metal, then it will be an autogeneous weld. So in a autogeneous weld, dilution is 100%. It means only base metals are contributing into the weld metal, right? Only so those only weld metal, only base metal makes the weld, in simply speaking. But if you are going for non-autogeneous process using a consumable, then your base metal will contribute to some extent depending on the arc energy, heat input, right? So this dilution have a significant effect on the microstructure and the property. You look at the two below figure, you see in the middle figure, second one figure, the joining of 6061 aluminum, you can see this is with V groove without root opening. So you say there is no root opening. So there will be a higher dilution from the base metal, right? Now you see the third figure, V groove without root opening. So there is no root opening. So you see the most of the time the blue color. This means there will be, or the weld metal composition will be more or like the filler metal composition. So it will be most of the like undiluted undiluted filler metal composition, or the weld metal chemistry will be very near to the filler metal composition. So design is also important aspects, but this dilution has to do with the weldability, because the contribution of the base metal into the weld metal will change whole scenario, its microstructure and their mechanical properties. Most of the time, we use the compatible filler metal for the joining of two similar metals and two dissimilar metals. So this is a case study to understand the uh, two different metal 74 pH, that is 70 chrome, and for nickel precipitation hardened metal grade steel and stainless steel type 304L. This is a case study. I used to solve such case studies. So it is a filler metal using ER630 is a filler metal of choice for this application. Now this is a WRC 1992 diagram, right? So this is a theoretical estimation. This will give a theoretical estimation of the weldability. It means whether the weld produced with ER630 filler for two base metals 74 pH and 304L will join successfully without cracking or not. So here again we will we will calculate the chromium equivalent and nickel equivalent. Chromium equivalent contains chromium and molybdenum and niobium of the base metal, and for the filler metal we employed, and nickel alloy with nickel, carbon, nitrogen, and copper will be considered a nickel equivalent. So we mark the points of the composition on the WRC 1982 diagram. Say for 304 air will stand here, and 74 pH precipitation hardened grades will stay here. Now we will consider a equal mixture or a equal contribution from the 304 and 74 LA, right? The equal contribution, 50% from this one, 50% from this one. Now ER630 filler metal will come somewhere here. Their composition will come somewhere over here. Now we will connect this point with the middle of this line, right? This lead line. So what will happen depending on the dilution? Say it is a 30% dilution of, or if it's a 40% dilution, 60% dilution of the filler metal. So when your base metal is contributing 15% most of the time, 15 from this side. So 15 plus 15, 30, right? So assume 30% dilution. Now filler will be diluted by 30%. It means filler will contribute rest of the amount. So filler will be 70% and 15 will come from the either side of the base metal. So you may consider a point where you have your weld metal somewhere here, right? So your weld metal will somewhere here that will show that is fall in the region of the martensite boundary. So you can definitely say that it is not without risk, right? This analysis shows that the weld joint is not without risk. It means there will be every chances of heat affected martensite development, heat affected zone, and there will be a cracking, right? Because of the thermal cycle. So it's a theoretical estimation of weldability, right? And these AAF, FAF, these are showing different solidification modes, right? So actually, looking at the time, I will not be able to discuss this WRC 1982 diagram in detail, but sometime other, I will explain this in some program like this. Okay. Now, this simply to explain you about the theoretical estimation of the weldability. First, for carbon steel, low alloy steel, and say you go for the carbon equivalent formula, and you calculate the composition, and you decide whether your steel is weldable or not, whether it is weldable with preheat or atmospheric treatment practices. Then, if it is stainless steel or duplex or ferritic austenitic stainless steel, then you go for this WRC 1992 diagram developed by Welding Research Council. Or there are various such predictive diagram. For ferritic martensitic steel, you go for the Belforth diagram. For superferritic stainless steel, you go the APSI diagram, right? Likewise, there are many such predictive diagrams. This will you give a picture or estimation whether the base metals are weldable or not, or if they are weldable, they are with a risk of crack or not, right? Okay. Now moving further. Now, having discussed this theoretical test, now you may now realize that this theoretical test like what we have gone through, right? Carbon equivalent and those assessment on the WRC 92 diagram will not take into account of the welding variables, right? Indirectly, we assume any, say, dilution depending on the heat input. But during the actual welding process, heat input has a tremendous effect, right? So during the actual welding, where input may be different, right? So these predictive diagrams will not give a clear picture, but they are most of the time used for the predicting whether the materials will be weldable or not. In fact, otherwise, you have to go for the actual weldability test. You have to go for the procedure qualification test, right? You have to prepare the test coupon. You have to go for the procedure qualification test. If it satisfies, then your welding procedure specifications are approved. So, and this will not take into account the welding variables, effect of preheat, electrode, composition, and such many more things. And to add on the top of it, residual and reaction stresses and hydrogen induced and other conditions. During heating and cooling, what will happen during heating? You may consider welding as a small, it's a localized heating and cooling. Unlike your casting, in your casting, you have bulk heating and cooling phenomena. But in a welding, you have only localized area which is being heated and cooled. So because of its localized heating and cooling, what will happen during heating? Material try to expand. So surrounding material will not let it expand properly, right? And same thing will happen during cooling. During cooling, contracting stresses will be developed. So surrounding base metal will not allow it to shrink properly. So as a result, what will happen? There will be some residual stresses remain on the weld joint. Most of the time, tensile residual stresses are on the weld joint. So these residual stresses are, if they are not relieved by means of post-weld heat treatment or by any thermal means, right? There are various methods of relieving the residual stresses, right? And measurement of residual stress. But if they are not relieved, I mean to say that, then they will also aid into the poor weldability. They will also aid into the crack phenomena, right? They will also result into poor weldability. Then hydrogen-induced cracking, of course, because this hydrogen has tendency to lodge or to accommodate into the most disturbed microstructure, and your martensite or your most residual stress microstructure will very potential site for the hydrogen. Okay, then visual tests can be used as a weldability defects are often difficult to see because with naked eye you cannot estimate the some minor cracks, some hairline cracks, or some porosity or inclusions or residual stresses, right? Okay, so we are preferring actual welding test. Now, how can I assess the weldability of a material? Now, question comes: how can I access? So, weldability assessment. So first, before we go for the weldability assessment, we should keep in mind the three things: the degree of tolerance that can be allowed for the purely metallurgical defects. So I'm sure in my previous in the previous lectures you have understood about some defects produced due to metallurgical defects. Some are the operational defects, right? Metallurgical defects like inclusions, that process related, like porosity, cracks, and slag inclusion, oxide inclusion. These are the metallurgical defects. And the operational defects are like, the gas pockets or the, say, maybe cracks or fissures, like this. These are the process related defects. So first we have to be sure about the degree of tolerances, right? Whether we will allow these defects and to what extent. So there are many, there are standard established welding codes that will guide us about the degree of tolerance. It means these defects, the size of the defects, the orientation of defects, and depending on which we can qualify our or we can approve our material for production, right? And of course, there are for after welding, there are also standards available, AWS and ISO standards. This will guide us about the degree of tolerance, right? And type of test that will be suitable in the circumstances. So that will depend on the geometry of the fabrication, material, and the circumstance, like what are the position under which we are welding, right? So that we will be discussing during our presentation. Okay, now first fabrication test, right? Because fabrication tests are meant for determining the susceptibility of the welded joint to cracking, and they are grouped into various three main thing. First is hot cracking test, second is a cold cracking test, third is a test related to crack associated with the specific fabricant conditions or structures. Now, third is a very specialized or very customized test, right? And first and second, hot cracking test and cold cracking test. So, before we go further, what is hot cracking test? It is the crack that may take place during or immediately after welding. That is known as hot cracking test. What is cold cracking test? It is the delayed crack, or it is the crack that may produce after the welding is over. It may happen anytime after the welding is over, right? I mean, few seconds, minute, or hours, or months, or any time. It is not a cold cracking test. Most of the time, hydrogen-induced cracking, right? And third is a customized test, right? Depending on our requirement. Okay. Now, fabrication weldability test under the hot cracking test, there are various standard tests like Murex, Holdcraft, West Trend test, ring weldability test, Sigma jig test, and hot ductility test from A to F. And in a cold cracking test, there are tests from controlled thermal severity test, CTS test, Taken test, Lehigh restraint test, longitudinal bead weld test, implant test. Now, we will be able to, I'll be able to discuss A to E, means under the red square, and for cold cracking test, this A and B and D, right? So, if time permits, we'll be able to complete. We will be able to go through all these tests, but these are the most popular tests, and out of this, I would say this Western test and Sigma jig test, West test, and the developed version is a ring weldability test, and the Sigma jig test are most popular. They are used most of the time. And for cold cracking test, the CTS test and Taken test, and to some extent longitudinal bead weld test. But these are the most important tests I am going to discuss in presentation today. Okay, now to begin with the Western test, the first of hot cracking test. Okay, so sorry, my slide stuck. Okay, now various trend test. Now you stress the word various trend. The word variable, VS comes from the variable, and restraint comes the restraint, right? The various trend test. So you can understand from the first uh, impression that this is a test this is the test in which we have to vary the restraint. I hope you, being a metallurgical and mechanical background, particularly with a mechanical background, you better understand the restraint, because I have just mentioned you about the say the restraints posed by the surrounding base metal during heating and cooling, right? So we are inducing a mechanical restraint over here. So to assess the weldability of a material under the mechanical restraints. So, you know, in long back in the mid 1960s by W.F. Savage and UD from the Rensselaer Polytechnic Institute, they have designed weldability of materials in terms of hot cracking tendencies. So they were first to term the hot cracking tendency, right? So this test is used to quantify and rank a material susceptibility to hot cracking. So when you have a numbers of materials, these their guidelines are available that you can rank a materials depending on this susceptibility to hot cracking. And then modified version, many modified version, or there are many extension and many modification to the basic Weierstrain test. We'll discuss this one by one. Longitudinal, then comes transverse, then spot, and these all were developed gradually over a period of time to quantify effectively a, uh, a mechanism, or to assess the mechanism of the crack. Because as you know, most of the time this crack is developed because of the eutectic liquid, right? I had mentioned you previously that because of low melting point film, because of low melting point elements, presence of low melting point elements in the solidifying weld metal, the grain boundary will be wet by the eutectic liquid. So it backfills the crack as a function of eutectic composition. So the eutectic composition is very uh, interesting to know, and most of the time many research are ongoing, and there is a plenty of research scope in this area even today, right? So okay, so moving ahead, the first and most basic test is a Weierstrain test. Okay, now this Weierstrain test basic setup is look like this. You can see is a what you see in the left hand side figure is a 8 by 4 each plate, and you see the weld is joined longitudinally, and this plate is fixed over here. Now it is free at this end, just like your cantilever beam. And when your arc will move from this end, so from the free end to this end, most of the time, what will happen? Uh, there will be a so through with the help of the plunger from the top, it will be bent on this die. This die will have a designed radius on which it will be bent, and you will be studying the area, particularly this area, and this is the area of interest, particularly your molten weld pool. Now, this molten weld pool is area of your interest, and you will be studying this area. You will be check it for the development of the crack, right? So you better see this is an enlarged view of this. You can better see this. This is the weld deposition started from over here, and this is the position where the weld ends. So by the time it's solidified, and the force will be applied at its free end. So as a result, what will happen? There will be a sufficient amount of strain. We'll call it as an augmented strain, right? Strain will be developed on the fusion zone and on the heat affected zone. So uh, on account of susceptibility, also, or say as a function of susceptibility to crack or the chemical composition, material will develop, may or may not develop crack. So is a side, and this is a top view of the original longitudinal Weierstrain test setup, right? Now, this area you can see, this is the area where the weld ends. You can see the crater, right? Where the arc ends. So there'll be some depression. And this is the location of the arc, right? And these are the heat affected zone crack. It is level. And this section is removed from the observation. Now this section will be removed for the, say, from the visual and microscopic observation. Now we'll move further. Now this is the longitudinal Weierstrain test setup in a 3D picture. You would see a GTAW torch, which is moving from this end to this end. Now you see the arc is in action, and you better see that this plate is fixed at one end using this fastener, using the simple bolt. or on the top plate of it, and this die is having a particular radius. Now the mechanical force will be applied as soon as it reach at the predetermined location, and under the effect of force, this plate will be bent on the die, and you have seen the rest, right? You have seen this area or the particular this region will be taken for the study. Okay. Now this is a test setup for the longitudinal variation test. You can see because the weld is along the longitudinal direction, right? So simply it is known as longitudinal variation test setup. Now this is the original test. So it is the same information which I have given you. And this type of test produces cracking in a both fusion zone and adjacent heat affected zone. So you could see this from the previous picture. There's because of the bending stresses, bending stresses produced because of the applied force from the top. What will happen? This area will be bent, and so this fusion zone and the heat affected zone will be under stress. Now, moving ahead, what will happen? What do you see that it is sometimes, very essential to know whether the crack is originating from the fusion zone or from the heat affected zone, or whether it is a HSZ liquefaction cracking or a solidification cracking. Because we knew from the previous slide that this solidification cracking is taking place in the weld metal most of the time, and this liquefaction cracking is taking place in heat affected zone. So it is difficult to separate out, right? So this is a limitation of this test. So spot and transverse tests were developed. So now the modifications, because I told you that over a period of time, from the basic test setups, many modifications were made, and out of these spot and transverse tests were developed. So this is a setup for the transverse test. Now, what do you see? What is your first observation? Your first observation is, the position of the welding direction is changed. Now, instead of longitudinal, it is transverse. That is first observation, right? And the die is put on the well below on the weld line. And instead of pressing the plate from the free end, there will be two free ends on the either side of this weld line or the weld joint. We used to apply force from both the ends. So what will happen when we apply from the both? What will happen? This will not only producing on the fusion zone, but on the this heat affected zone as well. And you would see that these thermocouple are attached here with. So using the thermocouple, we can also measure the time for the solidification, and from the TS to TL. So from the TL to TS, from the liquidus temperature to solid temperature time. So the more accurately we can find out under what regime, under what temperature fall from the liquidus to solidification temperature, the crack will develop. Right. So these are the modification these are the latest development in the basic Weierstrass test. So this is a transverse test, and next we are going for the spot test. But before we go for the spot Weierstrass test, let's just take a look at this small test video I have found from the YouTube, just to have a look or to have an idea about the how the test is being performed. So I'm going to play the video. Please let me know it is working. Sorry, the screen is appearing. Can someone confirm me?
No, sir, it's not visible because you have just shared the Microsoft PowerPoint presentation screen only. If you will share your entire screen.
Okay. Okay. I think I need to share the screen for video, right?
Yes,
Okay.
yes, sir.
Okay. Fine. Okay. And now I got it. I think I should stop share, and I need to share video again. Okay.
Yes.
So video of the, just wait. Okay, I'm going to do this. Please spare me 2 seconds to do this. Okay, I'm going to share. Now, what I'm going to share is a VLC screen, media player screen. Okay, there we go. I think now the screen is sharing, right? Am I right?
Yes, sir. Screen is visible, sir.
Screen visible? Okay. So, okay, fine. Let us go through this video. So you could see a positioning of the torch. So you could see a transverse resistance test. Now the arc is started and welding is started. Now, as soon as it reach at a certain position, there will be a pressure from both the rod, from the both its ends. Oh yeah. Oh, now you see a literally sound of cracking, right? Now you are going to see what actually happened on the top. I hope this video will take us over there. Let us take a look. Oh yeah, see. So did you see the kind of cracking? Yes, here over a small crack, right? A very small crack may not be clear. Okay, would you like to see it once again? Okay, please have a look. Oh, right. Okay, and now there are many such videos on the YouTube. You could have a look to it. I could only include this transverse resistance test video for you, just to give you an idea about the. You see this is a mechanical. You see a thermocouple wire, right? This red and blue color. Sorry, I was late to show you, but I think you must have observed it very closely. You must have observed test setup. And okay, now I'm going to stop video and I'm going to, sorry, I'm going to share my screen once again. Okay. Sorry, I think I need to go to the slide where I have stopped. Okay, there we go. Okay, I was here. Okay, can someone please confirm me whether
Yes, sir.
which
Yes, it's
slide
visible, sir.
visible? Fine, great.
Yeah.
Okay, so you could see, right? And there are many such videos available on YouTube. Now, YouTube is a big source for learning, and there are many videos from the TWI, the Welding Institute UK, and from the various research labs. There have also YouTube channels like this was particularly from the lab of Dr. Adesha lab. I must uh, I must cite his work, Miss Courtesy. Okay, now, okay, next, transfer stress applied to bending stress across the weld and restrict the crack to the fusion zone, right? So there is little or no strain applied to the heat affected zone. Now, you would see that it is in the transverse direction, right? So most of the time, what did you see that most of the stress will be concentrated on the fusion zone and less will be on the heat affected zone. So there was a further modification, and the modification is a spot Western M test. M stands for the modification. So it's a modification to the original test where you would see a only spot is bad, and, this spot will develop a spot weld, and this small spot weld develop a susceptible adjacent microstructure. So you will simulate a heat affected zone using a spot weld, and this spot weld will have a adjacent microstructure. Now, the test setup is something like this. You would see in a picture. what do you see? That instead of making a weld on the line, you would see only, sorry. Okay, you would see that only and only the weld is made on the spot. So I'm trying to do this cursor. Okay. Okay, it automatically went up. Okay. Now you would see that only spot is weld made, right? Now this, you must be seeing that there is a HZ crack. So this is more accurate test to judge the susceptibility of cracks in the heat affected zone in comparison with the previous test, transverse test, right? Because limitation on the transverse test is that most of the stress will be concentrated on the fusion zone. Now, this test will produce stress on the heat affected zone. So it goes with the same test setup, right? And now you see a formula over here. I'm coming to this formula, but this is a schematic illustration of response variation test setup. And this all source I have taken from the Weldability of Metal, Dr. J.C. Lippard book. It's a very popular book, Welding Metallurgy and the Weldability of Steels. At the end of presentation, I will also um, mention his latest work, the weldability, assessment of weldability, the area of weldability of metals. Okay. So now you see this is a picture from the same. So this is a picture from the same book. It is a 8286 stainless steel with at 5% strain. You know, the strain is also calculated here at a 5% strain. You would literally see a crack in the heat affected zone, right? This is a HZ, and this is a spot. This is a say weld nugget, and on the surrounding it, you see less dark region is a heat affected zone, and this heat affected zone, the crack is formed, right? So is a spot variation test sample on a plan view. This is sourced from the same book. Okay. Now you would have seen that in most of these test GTA welding process is used, but you could also include other welding processes. First, the standard is GTAW welding process. Otherwise, you could customize it using your other tests as well. But this could be without filler metal deposition. So these tests are usually autogeneous in board because you did not see any filler metal, right? You did not see deposition of any filler metal or a dipping of any filler metal into the weld pool. It all only arc is generated and the arc is directed on the work on the test coupon and the test is conducted, right? But this filler metal deposits can be tested using this special test. You know, there is a provision that if you want to find the filler metal or the compatible filler metal, you could perhaps do this. You could perhaps first develop a molten weld pool, and you can dip your filler metal just like GTAW standard practice. You can carry out this test with the help of filler metal. So you can qualify filler metal for the particular test setup. And the bending is normally very rapid, right? It will 2 to 10 each per second only. Now, right? So it's a very fast bending. You could see in a video. And now, the most important quantification part is here. The augmented strain is controlled by the use of interchangeable die blocks. Now, augmented strain is means, you know, the varying degree of stress. Because we have known this word like varistrain. So variable strain. So augmented means which you can keep on changing by changing the die blocks. Because if you employ a lesser radius die, then it will have a more strain, right, on the material or the test coupon. Likewise, so you change the die block radius, and accordingly your strain will also be changed. So that is why there is, and the strain level will be changed. So this strain is formulated by, or empirical formula is strain is equal to T divided by twice capital R plus small t, where small e is augmented strain, right? Augmented strain where small t is a plate thickness you apply, and R is the die block radius, right? So now you go on changing the die block, obviously, because your plate thickness, you can qualify for different plate thickness, because most of the time your qualification for various test will start from the more than 3 mm thickness. I'll come to this. So what are the thickness limitations, and how can we go for other tests for thin plate quantification, right? But most of the time you can start with 3 mm thick and more, and this R is a die block radius. So you can vary the die block radius, and since it is in a denominator, now you will see there will be a strain will be inversely proportional to it. So more you take the die block, more strain will be produced, right? It is simple formula. Okay. So now measurement of crack lengths on the surface of the astatic sample using a low power microscope. Now, how would you examine the crack? You would examine the crack using low magnification microscope, right? With a 20 to 50x microscope. And the total crack length is the summation of all crack lengths. Now, there are various concepts like TCL, total crack length, like MCL, maximum crack length. And the most recent is concept is a maximum crack distance, that is MCD. Now, most of the people measure in MCD, maximum crack distance. So previously, people were measuring the maximum crack length, then they were making summation of the different crack length. Now they come to a conclusion by years of experimentations that most accurate is to measure the maximum crack distance, MCD, through which distance the crack has been propagated, right? MCD. Okay. So sorry, my slide is not changing. Okay, now, okay, what is the technical concept behind this test? Because we have seen this test, we have in slides, we have seen a visuals also, but we should also need to understand the technical concept behind the test, right? So I included this technical concept because we are estimating the saturated strain. I hope you understand why the word saturation, because saturated is something which is a sufficient, right? Saturated means having complete in itself, saturation. So you look at this graph, which is developed as a result, is a maximum crack distance, this is MCD versus augmented strain. Now, when you plot a graph using these two, you would see that solidification cracking in the fusion zone there'll be some amount of strain already. That is known as threshold strain. It means you require some strain to develop the crack, right? There is only initial cracking. That is known as threshold strain. Now, you will be entering a different region. There's no augmented strain. It means you go on changing the die radius, and you will try to see after which level of strain your crack distance or your maximum crack distance becomes continuous, or it becomes constant, or a augmented strain level, right? So you could understand that below is the augmented strain. Now you go on increasing the augmented strain level. It means you go on changing the strain level, and you figure out that after which strain level your crack distance becomes constant. Maximum crack distance becomes constant. It means say 6 mm to 6 mm after this limit. So this is known as saturated strain. Now these saturated strains will determine the maximum extent of the crack susceptible region, CSR, crack susceptible region. So this will you can measure CSR, crack susceptible region. So this region is more crack susceptible, say 2 mm from the fusion zone, 3 mm from the fusion zone likewise. Now, this is the real picture captured from this same book. And you could see it's a type 316 stainless steel transverse very thin specimen. And here you see a fusion boundary and a heat affected zone. You could literally see a development of crack in the heat affected zone. And this is the, you could see there will be some crack which have propagated through the maximum distance. That is known as maximum crack distance, MCD. Okay, all right. So we'll move further. Um, Now, measurement of solidification cracking temperature range. That is most important. Solidification cracking temperature range. If you remember, I have mentioned you that there will be a certain range, say from the TL to TS, from the liquidus temperature to the solidus temperature, where there is most susceptible range. It is most, say, most dangerous range in which there is highest susceptibility for crack to occur. So this SCTR, solidification cracking temperature range, can be calculated using this formula. You have to calculate the cooling rate. The cooling rate you can calculate by means of, you have seen the test setup, right? You have seen there will be the thermocouple wire, they are plunged into the near the weld pool, right? So this will give a liquidus to solidify first temperature range, the TL and TS, and the time under which the material is cooled, say 4 degrees Celsius per second, 6 degrees Celsius per second, likewise. So range of this divided by the time, right? When you plot the temperature versus time plot, you get the cooling rate. So multiplied by the maximum crack distance, MCD, and divided by the welding speed or the welding velocity, right? In mm per second. So when you work out with this formula, SCTR is the cooling rate into MCD divided by V, you will get a solidification cracking temperature range, right? So for a stainless steel and nickel based alloy, their saturated strain level are generally ranging from 3 to 7%, and threshold strains are level from 0.5 to 0%. It means you require 0.5 to 2% of minimum stress to develop the crack, and there your sample made of stainless steel and nickel based alloy will show a saturated strain level. It means the maximum crack distance will become constant after, say, 7% of strain level, like as per this previous slide, right? I hope everyone understand this, right? Now, this is how the quantification is made, right? Now, in this graph, you will see a TL and TS, right? Now, when you plot a temperature versus time graph, right, you can develop this graph using your thermocouple. It means if you have a thermocouple and you have a temperature monitoring system and a stopwatch, these days, these are all automatically done. And this formula is also automatically calculated, but this is the technical fundamentals I thought to explain with the help of this very good written book. Okay, now you will see this TLTS. Now you see a cooling curve, right? You would literally see this is a cooling curve, because as soon as the weld joint is now, having calculated this MCD divided by V, the particular range, say 0.5 to 0.7, right? Most of the this value. Now, if you project it on the cooling curve, you see a solidification temperature range, SCTR, and most of the time you see it is between TL and TS, right? So you could figure out this SCTR by, say, multiplying the cooling rate with MCD divided by V. So as a result, you will see a particular band or particular zone where there is highest susceptibility for cracking, right? So this is the temperature range, temperature of liquidus, and this TS stands for the temperature of solidus. So you could see this is the range which is most susceptible in which crack can happen. Okay, now this is how it is calculated. Now, from the same book, I have captured a table, and these are showing a different welding variable to perform this test. Okay, you could see a specimen length 3.5 each. In mm is 89 mm. Specimen width is 676 mm. Process is GTW. Arc length is 1.25 to 3.8 mm. Hope you understand by the arc length, right? Is the distance from the electrode, tungsten electrode tip to the workpiece distance. Huh? Now, maximum voltage changes from 1 to 1.5 volt. Current is ranging from 160 to 190. Travel speed is 1.7 to 2.5 mm per second. And augmented state is 0.5 to 7%. Sorry. And this ramp time speed, bending, it is 150 to 254 mm per second. Okay, so these are the, for knowledge, these are some welding parameters for conduction of the test. Now, this is most important information I have captured from this same book, table 9.2. You would see there is also a role of a solidification mode. Because in your previous, very previous WRC 1992 diagram, I had mentioned about the, I have pointed out particular A, AF, FA, and F, right? So these are the different solidification modes. A modes, A means the weldment will be undergo solidification in the completely austenite. AF means primary austenite, secondary ferrite. FA means primary ferrite and secondary austenite. And when it F and it is fully ferrite. For example, austenitic stainless steels. Austenitic stainless steel like 304, 316, austenitic stainless steel, right? Most of the time solidifying into AF mode of solidification, right? And hardly in FA mode. But the ferritic austenitic duplex stainless steels are solidifying in a F mode. Likewise, nickel-based alloy, like you can see this 304 and 316 are a primary solidification mode. Understand this primary solidification mode, right? Are ferrite. So when the primary solidification modes are ferrite, there is no danger. It means solidification temperature range. You could see there is a less range under which they undergo solidification. So intentionally, I have marked this. Why I have marked this? To show you higher the solidification range, say 139, 418, there are higher range. 144, 145, 190, higher solidification range and higher the susceptibility. This could be with, you could see precipitation hardenable grade 8286, like where the primary solidification mode is austenite. It means when you have a combination of both on the second column and third column, when your primary solidification mode is austenite and you have high solidification temperature range, then your crack is certain. Right? This is the analysis of this chart, of this table. Once again, I'm repeating, when your primary solidification mode is austenite, for any austenitic or nickel-based alloy, right? Most of the time. Austenite, you say 304, 316, 3110, 8286, there's a precipitation grade, the nickel-based alloy, C20 to 617, alloy X, and all this. They have a, if your primary mode of solidification is austenite and they have a high solidification temperature range, that is SCTR, then your crack is certain, right? So you have to do something to avoid the crack, right? So you read this the below line. The SCTR data allows a straightforward comparison of cracking susceptibility. This value may also allow alloy selection based on the restraint condition. Now you could choose the alloy depending on these guidelines, right? Now, if your restraint is very much high, then you always go for 304, 316L and you will not go for 310. Because if your mechanical restraint is high and your microstructure is susceptible, then you are going nowhere. Right? You have a high solidification temperature range and you have a susceptible microstructure, then your crack is very certain. Then this, if you are going for a high restraint condition, if you are going for low restraint conditions, say your mechanical restraint is less, it means when you are repairing your weld, you are providing a condition under which you are performing a weld where there is no mechanical restraint or the material have less restraint to mechanical force or say, then you can go for 310, but it's not advisable because of the highest certification temperature range. Same goes with the nickel-based alloy, right? I have not marked this point, but same story is gas for. But this lowest certification temperature range, 31, and which ferrite mode of certification, more than safe. 50, almost safe. 58, almost safe. But these are not safe. Right? So this is, I would say, this is an important slide of this talk today, because my idea is to throw a light on the say assessment of weldability, how the assessment details, and particularly how you should choose the alloy, right, based on these guidelines. Okay, so this is like this. Here the note is also written: SATR value below 100 degrees Celsius may be required to prevent cracking, while low restraint weldment 150 to 200 degrees Celsius may be sufficient. For low restraint, you can go for this, but for high restraints, you are not recommended. Okay, this is the say. This result is from the years of experiment or various efforts and contributions from the worldwide researchers. Particularly, Dr. John C. Lippert is one of these, right? He's from the Ohio State University. He is now emeritus professor in the metallurgical engineering department. He is now retired, and this capture is from his book. So big thanks to him for providing the source, right? Okay, now this is a circular patch test or ring test, right? As for assessment of the certification cracking phenomena in austatic stainless steel and aluminum welds, because they are more susceptible to this kind of crack. Now, circular patch test is removed from the center of the test material, is imported to a large restraining plate. Now, you have first take a look at this. Now, how this test is performed? This is another test, circular patch test. It is meant for austatic stainless steel aluminum welds most of the time, and most of the time it is done in the industry, is industrial practice. What they do, they will people here may start with some block of say 1 inch or 1.5 inch or say 2 inch thick block. Now there'll be a test sheet. This is a test sheet. Now the test sheet will be fully fillet weld with the base plate, and there'll be hole through which there'll be hole, and the nut will be passed. Sorry, bolt will be passed, and the nut will be uh, fitted on it to induce some restraint, and surrounding it, weld will be performed. Here you can see the torch, right? Tick torch making test weld. So you could see this tick torch is moving around this, this bolt, and it is producing a test patch, right, on the test plate, not on the base plate. And this is a restraining bond. Now you are producing a restraint condition using this. You are simulating this condition. Now you can understand this test material is positioned so that gap around the test patch is constant. Because you would see the gap is continuous, right? Gap is constant. Now from all sides of the test piece, you could see that the distance is same, right? Now, weld is between the page and the original plate is made following the circumference of the page. How it look like? You see, this is from the research paper from from the book of Shinto Kao. He is also a well contributor author in the field of welding metallurgy. And this is a color picture of this. You will literally see a test place made with a hole, and this test place is now disassembled. So you would not see a bolt on it, and you could see around it the weld is made, and to add in that more, you could literally see a crack. आप crack देख सकते हैं, right? You could see a crack, and this at a scale of 10 nanometer, you literally see a large crack of centimeter size, right? This is a certification cracking in circular patch welding, right? Now this a figure with 1100 L and on a circular patch welding of 3.2 mm thick 6061 aluminum with filler metal 1100. So this base rate was 6061 say aluminum silicon magnesium alloy, and 110 is the filler, right? Another case is a hot cracking test or Burek test. Now this test setup is rather uh, is not say complicated to understand, but you will see a plate of say 10 to 50 mm thick, and their test plate is 50 to 70 mm in width, right? So what do you see? You see two plates. This is plate number one. Plate number one. This is plate number two. Now these are one is a fixed clamp and another is a rotating clamp. So it is showing the rotation in this direction. Now it is rotated after a certain time. The electrode is now used for impinging the arc on this uh, particular fillet, right? This is a you can see is a convex fillet is made, right? So these are two members, plate number one, this is plate number two. The plate number one and two are mostly 10 to 15 mm in diameter, and there are generally 50 mm in width. Now, at this, the corner is now fillet welded. Now, having finished this clamp with this rotating tab, this clamp is a fixed tab, right? Now, there will be some rotation. Rotation will be limited to the 30 degrees maximum. Now, after which there'll be crack will be developed in this fillet weld, and this crack will be assessed. And this is type of test done is for most of the time for carbon and low alloy steel weld deposit with coated electrode like SMAW coated electrode. So if you want to figure out uh, the say weldability using the coated electrodes on a carbon steel or low electrodes, you will go for this test, right? But you need a fixture to carry out this test, so fixed and rotating clamp. Okay, this is known as Murex test. That name is in honor of the inventor, but it is typically under hot cracking test category, right? It is same information. After 5 seconds, it's bend, and 1 degree second, and rotation is 30 degree, and strain is developed, and the length of crack is appeared after straining, and it is measured. So this test is used for obtaining the comparative information on similar or dissimilar welding failures. It means if you are joining two different materials, the carbon steel, stainless steel, and if you go for if you go for 308, 309, say, and if you want to figure out some correct substrate with 308, 309, or 310, then you can go for this test. Comparative information, but you can use the different brands of different brands of or different manufacturers electrodes and have a comparison on the ductility of the weld metal, right? You could do this using this Muret test. This is a practical application. Now, next is the Holdcraft fishbone test. Now you understand the word fishbone. Sorry, this is appearing from the top. Okay, fishbone test. Now, this test plate is of typical type. You could see a test plate is how it is developed. That initially you saw that it is saw cut. Saw cut, you can understand being a mechanical person, right? Saw cut means with a saw cutter, there is some cutting equally on both the side of the plate, and this cutting will be the length of the cut will be increasing as you move from the around the certain direction, from say this end to this end. This correct length will be increasing, saw cut depth will be increased. Now you have start your welding from over here. This is your welding direction, right? This is a preferred welding direction. What do? You are moving particularly from in increasing in an area where you have a high slope cut depth, or you have a minimum area. Say, putting it another way, you have less material available for throw the heat. It means when you are moving your heat source from this end to this end, your heat should get dissipated from the plate. Are you agree with this? Your आपकी heat जो है, your moving source heat should get dissipated through the thickness. Now the thickness or the volume available here is very less. You have no volume available here because of this because of this cut length, because of this, cut, because of this vacuum, because of this non-availability of the material. So what will happen? What will happen in this course? Your strain will be increased. So this is a typical Holdcraft test setup. You could see a tick torch, and this tick torch will be moved on, and this will have a particular dimensions and a particular socket width and at a distance over which these crack or socket are made, and you will move your heat source, you will move your electrode or sorry arc from here to here. So in a decreasing specimen stiffness, right? Now here we can understand. This test is developed by Holdcroft to test the workpiece in form of thin sheet like aluminum material susceptible to solidification crack. If you are working with a thin sheet and you want to find out the susceptibility to solidification crack, the test is ideal test. This is a customized test, right? Specimen is free from any constraint and without any clamping. Do you see any clamping? Do you see from where the material is bolted or is fixed from any of the end? No, it is a free end. It means plate is simply put on, or the sheet is simply put on the plate material, or the test plate is simply put on, and the welding is performed. But provided the plate is uh, previously machined, right, according to the standard dimensions specified in the standard, right? Slots of increasing depth are cut into the workpiece from its two opposite sides to allow the tensile stresses. Now, this is very important information to allow tensile stresses to gradually decrease along the weld and hence the crack to stop. Now, there will be a tensile stresses will be developed. What will happen? Because you have no space available to distribute your stress, right? Because as you move along, these tensile stresses will be developed because the moving heat source or the weld pool will try to contract, and you have a resistance to contraction because of the less bulk metal volume available surrounding it. So what will happen as a result? You have a uh, decreasing tensile residual stresses, right? So now, without the material remaining between the two slopes, help absorb the heat. This is something I have mentioned you. The crack length along the weld is used as index for the crack susceptibility. Now, whatever the crack length you examine over here, right? From you start with this. So initially some slot will be cut to facilitate the crack tip to propagate. This is a process fundamental, or this is a standard procedure. Initially 225.4 mm length of 1 inch and 1 mm wide crack length is initially made so that the crack can be propagated from this end. And you will examine the crack length as you move along the weld. And when you stop over here, most of the time your arc is stopped. So this is the 11th slot starting from this end, right? This is a Holdcraft or fishbone test is the index for the crack susceptibility. Crack length along the weld is the index for the crack susceptibility, right? This is a source from the Shinto Kaoru. Now, sigma jig test. This is a most of the time latest test developed by the Oak Ridge National Laboratory. This is the latest test because it is overcoming the limitations associated with the Western testing, particularly thickness limitations. I would not say the Western testing is no more valid test. It's a very much valid test. It is most accurate test to assess the accessibility of materials, different materials. But it has the limitations associated with the thickness, particularly thickness greater than approximately 3 mm, right? You can go for the Western test. But if your thickness limitation is less than 3 mm, right? Okay, Patterson, I got it. I think I'll be at your presentation, no problem. So if your thickness limitation is more than 3 mm, you will go for other test. That is a sigma jig test. So the sigma jig test, you can go for thin sheets of materials like 50 by 50 mm, and then be clamped in fixtures. So noted down is organic restraint test, mechanical restraint test. and the transfer stresses will be applied on the post with the instrumented bolt, and bolts are instrumented with the strain gauge, so you can measure the amount of strain developing or induced in a say test plate. And this test is producing autogeneous GTW process to make the one on the center line. And welding current of 20 ampere is used to torch along the 15 mm per second is the traveling speed. And not only one but multiple coupons you can evaluate and in the round of the test when you run this qualification test. And when you run when you go for the multiple coupons, you have to identify the low stress level or the first test sample. Then this will be linearly increased in each subsequent sample until centerline weld solidification crack is initiated. So you first start with the test sample. You start with the low stress level. I mean to say, you first start with the low stress level, then you start increasing your stress level, and you go in increasing until your centerline weld solidification crack is initiated. It means you start with say 3%, 4%, 5%. Say at 7% or say at 11% your crack is appearing, then this is your stress level, right? So this is a diagram of a sigma jig test. You would see it. This is a test plate, and it is fitted with the help of no, this is the area, right? This is the area of interest, and this is a test plate. These are mechanically fixtured. Now, if you would see this fixtures, you would see in a side view, mechanically clamped to induce the strain it. And this is a threshold strain, right? This is starting stress. You would now find the susceptibility. Now you look at this curve. The curve at the bottom showing the lower susceptibility, but this is showing the higher susceptibility where the percentage of cracking is very high, right? This is right. So this is a percentage cracking versus applied stress. So you start with the lower stress level and you come with the threshold stress limit, right? When you cross the threshold stress, you can judge the higher susceptibility limit, right? This is reproduced from this one technical article on weldability of nickel-based alloy, and this sigma jig test is a very latest test in weldability test of material. Now we'll move to a cold cracking susceptibility test. So I think I need to conclude the session in 10 to 15 minutes. So, you know, until now today we have discussed about the hot cracking test. Now we'll go for the cold cracking test. So you know that cold cracking test will examine the susceptibility of material, particularly for the hydrogen-induced cracking, right? Because they are delayed crack. They are not taking place immediately during or after welding, but after some time of the welding in a cold cracking conditions. So on a cold condition, so then a cold cracking susceptibility test. So this is our most of the time focus with HZ cracking, and there is a CTS, control thermal severity test is there. So okay, so now this is a test setup for the Taken test. You can see this is a typical test setup where the root is particularly slant. It is a Y shape. So it's a Taken shape, Y shape. You fill the material, you fill the material, and you have to first make the anchor weld. I'll show you. This is a typical test setup, and this is a section AA. In a section wise, how it look, and this is a section BB. You can see this is a weld. This is a finish weld, and this is a weld groove only. There's a geometry, and Taken test is used to examine a single run but weld, determining the preheat temperature required for the test condition. Because when you have a preheat, you will see that the solidification time or this cooling rate is controlled. So your hydrogen have a chance or have an opportunity to escape out of the weld material or the weld metal. So as a result, there will not be traces of entered hydrogen, and you will be free, or you will be away from any possibility of hydrogen-induced cracking. So this is the objective of the test, and this number of the test coupons, you can go for 1, 2, 3 for each condition, and you can decide the preheat temperature because you first start with some 25 degrees Celsius, 30 degrees Celsius, you go on taking different preheat, you go on checking out the possibility, but the test duration is more than 16 hours, right? Test duration is more than 16 hours because you have to see the cold cracking, right? You have to examine the cold cracking susceptibility. So you have to wait up to 16 hours time period to observe the test coupon for crack, for the development of a crack, right? Now, crack location is heat affected zone, obviously, because a thermal cycle is affecting most of the time heat affected zone where martensite would be developed, and martensite is a very hard microstructure and brittle phase. So hydrogen can reduce in it and can have more effect on HZ, right? Now, crack coefficient ratio of the crack length from surface to the weld cross-section area is a criteria for the cracking susceptibility. Now, another test is a controlled thermal severity test, CTS. So, controlled thermal severity test, I'll explain with a very short, in a brief, that when the heat is being, say, when the heat source is moving, the plate is throwing out the heat, right? So, depending on the section thickness, there is a thermal severity number, TCN number. So for a 6 plate thickness, TSN is considered by standard is 1. So TCN for the trithermal, it means when the thick sheet is there, thickness along the thickness and depth direction, it will be dissipated. So using this formula, you can calculate the thermal severity number, but for you can consider 1 for the 6 thickness. So control thermal severity number, how the test setup will look like. You have to just weld this test copper with the anchor weld. These are known as anchor weld, right? And known as restraining welds also, because here you are restraining the heating and cooling of the weld, right? Now, what do? First, you finish the weld. Now, in a particular fixture, the fixture is just like this. It is a fixture is a at a 45-degree angle. That is from the as per the AWSB 4.0. Most of the time, weldability test you will find in the AWSB 4.0, and you will when you finish the weld, you have to put the specimen into the water bath, keeping the weld joint part without touching the water, right? So in the this way you have to pull the weld or the test specimen. Then you have to section the specimen 1, 2, 3, 4, and use this A, B, these facing sides. You have to examine. So this is give you a picture. This give you an idea about the sectioning of the specimen. And after sectioning of the specimen, you can also go for the micro hardness measurement in the weld metal and the heat effector zone, particularly because this is a fillet weld joint, right? So you would examine this specimen for microstructure and for the micro hardness. Now, next and final test is implant test. Now, implant test is something implant. This word is known as when you have when you have a implant something, when you have included foreign body, right? Now, on this typical type of test, you will make a gap, and on this gap, you will put a specimen, and you will perform welding over here. So now, what will do? This is a welding. This is the top portion. This is a say section image. Now, what do? You will conduct this test. I mean, you will perform this test, and you will subject it to tensile stresses, and you will assess the say cracking susceptibility to the base metal, and the particularly this will be cooling down to 150 degrees Celsius, and the constant test load will be imposed on the specimen. This specimen is subjected to constant load like F. What do? You will apply the load and you will see where at what it cracks. Now, after cooling to room temperature, like below 150 degrees Celsius, you have to cool the test and you have to examine for the fracture, right? So it's showing the cold cracking susceptibility. So last is a Lehigh restraint test. It is same test but with a 2 grooves on the top and bottom with a 20-degree included angle and with a 2 as a fruit face and at a 6 from the bottom. You will perform this lehigh. Again, it is having the same kind of fishbone test arrangement, but this crack length is or the saw cut lengths are almost constant. They are not in increasing order, right? They are almost of the same size, but at a certain distance, say at a 37.5 distance from the each other. Now, this is information how you can do it, and crack identification is by NDT method. You should observe these cracks because when you perform this weld, you have to observe these cracks by the NDT method because these cracks are will be very finer in size, very invisible by the naked eye. So you have to go for the NDT test and conventional metallography examination to detect the test, and you can work out with chemical composition of the filler metal and base metal, preheating and input and weld bit geometries using this test. So this is another test are lamellar tearing and pre-heat cracking. These are for the heat affected zone. And one test is a through thickness ductility test. That is most the time for determining the lamellar tearing. Now, this is just a test schematic. You could see a in a not in a transverse area but in a longitudinal direction. Your specimen will be like this in opposite to the rolling direction, just like this. And this is a typical test specimen dimensions. Standard dimensions always given in A770 or 770 standards. And in the presence of any inclusions, in the presence of any metallic inclusions, this specimen will break early. So it's a lamellar tearing test, and test place is 1:25 mm thickness, and the accepted standards is that it should not exhibit not less than 20% of the specified tensile stress. So if it is a 240 megapascal, then 240 megapascal 20% rate, right? So 40% it should not show less than 180 megapascal strain. This is the measure of this through thickness ductility or laminar tearing measurement. Now last is the hot tensile test. Now this is a hot tensile test is conducted in the simulated well thermal cycle test. So what do? You apply a heating and cooling. Likewise, you see a temperature versus time. You see a heating, some and cooling between the 800 and 500 side. Okay, fine. So last test is a bend test, right? Actually, I'm running out of the time. I think by 5:30 I should conclude this. Now, this test is most accepted test, and in this test is more tweak, and most of the time this is done by the welding industry, a procedure qualification test, QW 160 bend test in the industry, 90 degree, 120 degree, and 180 degree bend test. Now, depending on this positioning of the root, positioning of the stretched fiber, either it is a root face or side. So for the thickness greater than 12 mm, I think you will go for the side bend test. And the acceptance criteria is this: thickness or say the crack should not have more than 3 mm in length in any direction, right? So the bend test is a satisfactory test in industries for measuring the soundness of the material. Okay, now coming to the next and latest part of our presentation. Nowadays, thermal simulators are available. So Global thermal simulator is a very state-of-the-art technology to assess the weldability of the material, and most of the investigations were contributed by Emeritus Professor John Lippard from the Ohio State of University, Columbus, USA. And this test, using this test, you can assess the stratification behavior, cracking behavior in the weld metal in the heat affected zone using the global simulators. There are different simulator versions are able to assess the test, resistance test, in a hot ductility test, strain to fracture test, reheat crack test, and all this, right? So if your institutions can afford this global thermal simulation, I would recommend you for this test. And these tests have been rather costly, but most of the times available with many leading institutions and say perhaps with IIT Bombay and many IITs, perhaps this thermal simulator is available. These simulators, you have a very high research opportunity using this state-of-the-art device, and you have a there is scope of plenty of research, building metallurgical research using this facility. So, as a summary, this is a variability test methods, various tests for hole cracking susceptibility, Lehigh resistance test for varimeter cracking, implant test for hydrogen assisted, oblique Y for the HZ cracking, for the cold cracking, and control thermal severity test for the assess the chemical composition cooling rates on hardness. Now, I have a reference for this welding metallurgical book. These are my references. And I would recommend you to read the Shindo Kao and Jesse Lipod and DJ Kotaki book. And one more, I have attended a global webinar using the global weldability by Emeritus Professor John C. Lipod. So some slides are also contributed to him. Credit goes to him. And these are the research papers of references I have. And most of the time, weldability tests you can find in the AWS B 4.0 standard. And okay, so at the end, I would say that one test is worth 1,000 expert opinions. So particular material is weldable or not, one should not go into the dispute and this debate. Debate most of the time consume most time. So instead, what you should do, it is better to go for the test, right? So it is my it's a advice from the anonymous. Okay, and you can visit my welding technical blog, weldingknowledge.co.in. I receive any technical query or technical issue related to weldability in welding metallurgy and filler metal selection on this blog, and I very much invite your question answer. So I'll be more than happy to handle your query, and I can try my best to provide any resourceful insights into your query questions. And now my session is open for any question.